So I think last class we have done extensive analysis for the VDUS and with the enthalpy departure and entropy departure. So I asked you to do for the departure for Payne-Robinson equation of state, and the Payne-Robinson is P RT B minus B minus AT divided by B square plus 2BB minus B square. It is PRUS, Payne-Robinson equation of state, and AT equals to ATC alpha T. Okay. So we know our formula, enthalpy departure, which is H minus HIG TP, which is Z minus 1 RT into plus B goes to infinity to V T dou T at B minus P D. Okay. So dou P by dou P dou T at fixed B for this case is R by B minus B minus dou A by dou T B square plus 2BB minus B square. Why? Because dou B by dou T at fixed B. That's why B is actually kept constant. Okay. So now you can see this is integral I. I want to find out I. So that's your task. I is B tending to infinity to B. B tending to infinity to B. T dou T at fixed B minus P at fixed T D. We also write fixed. So what will be your integral in the simplified form? Next step, I will tell you what you will get. You will get some down here, B tending to infinity to B, and then dB B square plus 2BB minus B square. What is that term? AT minus T, T of dou A dou T. AT minus T dou A by dou T. Next step, partial fraction. What are the things? There will be two terms coming up here, right? So AT minus T dou A by dou T divided by 2 into B, okay, into B tending to infinity to B 1 by B plus B into 1 minus root 2, am I correct? Yes. Minus 1 by B plus 1 plus root 2. Looks like you have done it. Good. Okay. And this factor is coming. If you do factorize, it will come. If you don't know how to factorize, you do Siddharacharya method. You will get the root. That is the way you can do factorize. Somebody can do directly, or you can do a Siddharacharya method. Quadratic equation: a square plus bx plus c equals to 0. Next step. I think you have done it. So, what I would expect AT minus T dou A by dou T 2 root 2 into B ln will give me in terms of Z.
Okay, Z plus capital B.
Okay, Devan.
So Z plus capital B into 1 minus root 2 by Z plus capital B 1 plus 2.
Okay. So you have done so much simplification. So VP by RT and all those things you have done. No, I have not approved what he is saying, but it is what we get Z RT. I will just give the step one after another. Did you get this much? Okay. Yes, Rahul.
So then we can take RT common.
Yeah, you can take RT common. So your departure formula will be, I'll give departure formula directly because since you have done it at home, it's good. Tp, which is z minus 1 RT plus T dou A by dou T minus AT divided by 2 root 2 into B, then ln, then it will be z plus B into 1 plus root 2 divided by z plus B into 1 minus root 2. Now it is agreeable, right? So similarly, one can get S minus Sij Tp. Okay, did you get the answer? S minus Sij Tp. S minus Sij Tp equals to R ln mod Z minus B plus 1 by 2 root 2 B dou A by dou T ln mod Z plus B into 1 plus root 2 divided by Z plus B into 1 minus. Quite easy, right? Good. Now we will go slightly different, as my friend already did it. Rahul already did everything here. So we'll go for the Gibbs energy departure. Okay, that Rahul you have done for all the equation of state. Peng Robinson. Okay, you have done that. You have given the formula. So maybe when you have time, you can give me at least Peng Robinson SRK. Yeah, Gibbs energy and most energy departure, not internal energy. You don't mean. Okay, so. Okay, so G minus Gij Tp, which is defined as P tending to 0 to P, we say Pi, dou G by dou P at Ti dP minus P tending to 0 Pi dou G Ig by dou P Pi. Right? And the formula, if you now I want to get this G minus Gij for example, the Peng Robinson equation. That will be one of the example questions, and that should be after the first principle. It is not that you get S minus Sij already from your exercise book. Just write the formula H minus T as I don't want that way. I want from this first principle. That's a good exercise. So, did anybody do other than Rahul the G minus Gij formula? Okay. What is just G minus Gij Pi? Basic formula is to do that. Next step. Dou G by dou P at fixed is B. Right? So this P tending to 0, Pi B dP minus P tending to 0, Pi B Ig dP, which is nothing but RT by. And as we decided that we won't go by see what Rahul we have done, slight mistake. We have used the VDP here. So it should not be done the VDP. It is V dou P dou V into dV. You got the mistake, right? Yeah. So what we have done here is not exactly correct. So this has to be converted to the V integral. This has to be converted to the V integral. So Rahul, I will give it to you this thing. Please correct and give back to me. This one. So do everything in terms of V integral. Of course you will get the same result, but it is not correct. So I cannot evaluate this. Okay, thank you. Give it to me on Monday. Yeah. So this has to be going to P tending to 0 to Pi. You go to dou P dou V dV, and then P tending to 0 to Pi, which is we have RT by P dP, and then again we have to put in terms of between infinity to Vi, to Vi. And what actually I am expecting that we will be getting a formula from this, and now what is the formula? What is the formula? How can you deduct from G minus Gi Ti Pi? Because that this G minus Gi Ti Pi, one thing I want to tell you that G minus Gi Ti Pi, which must not be equals to G minus Gig Ti Pi. It cannot be. So get the formula. So I ask that find the departure, this penalty departure from the based on the Peng-Robinson equation of state. Okay, so that is the structure of the question. Okay, so I hope you can submit on Monday everything. Enter bracket. So make sure that wherever the P is coming, there's a mistake we have done. It should be done in a P plane. You should in your answer never ever you should have P integral. It's better because of some confusion, sometimes you may use P integral, but while you take the risk, you may eventually get the same result, but always to go for the V domain. Okay, so I think this will be the ending of the entire departure exercise. I think I have done quite a lot of departure. I have given the full insight of the departure, how the departure looks and how it can be applied. Various aspects, starting from the first principle, putting the values like H minus Ts, you can get use energy departure, all those things I have covered. So next, we will see how this departure could be used in practical life. We are all practicing engineers. I am doing mathematics fine. Classroom, IT Madras gave me. You are also nicely in the classroom, and we are doing mathematics. But that is not the end of the story. After MTech, we have to go for job. And of course, nothing what I am discussing now, which will be useful for your job. If a guy will ask a question that what all you have done thermodynamics, you will proudly say, oh, I have done Legendre transformation, I have done these mathematical derivations. You can show a whole lot of maths. The industry guys don't like it. They will say, well, just close your math book, close your own math. What is the application? You might have heard the steam table, right? You might have seen steam table. Moiler diagram. Now we are teaching how the departure function will be useful to draw Moiler diagram and to draw the steam table. So that's the way we can actually, in fact, we are glad to say that, in fact, this approach of departure to have this steam tables and Moiler diagram, we chemical engineers do very detailed compared to mechanical engineers. So if you look at your problem set 3, number third problem. That's exactly the problem I have given for you to practice. Problem number 2 you can practice your practice home. This is a numerical plot. It's not a big issue. That's why I'm skipping problem number 2. Problem number 3, develop a thermodynamic property chart for oxygen for the temperature range minus 100 degrees centigrade to 1 degree centigrade and a pressure range 1 to 100 bar. Calculate the compressibility factor, specific volume, molar enthalpy and molar entropy as a function of temperature and pressure. And also prepare a pressure volume plot, that is PV diagram, pressure enthalpy plot, PS diagram and temperature entropy plot, TS diagram. Okay, those diagrams are actually useful for the refrigeration that we have seen. And we can actually, in fact, I will discuss the algorithm here. Of course, quote unquote, I will not ask you to write. If you are interested, write the program. You can go back home and try to develop your own quote unquote or MATLAB program to see the diagram how it will look like based on this departure formula. Okay, let's look at the problem what you have actually given. So it is how to solve, how to attack how to approach based on our departure, based on the departure formula. So assume oxygen, obeys Payne-Robinson equation of state. Payne-Robinson equation of state, and has an ideal gas heat capacity which is given by CpIg Joule per mole per degree Kelvin, which is 25.46 plus 1.519 10 to the power minus 2p minus 0.7151 10 to the power minus 5 p square plus 1.311 10 to the power minus 9 p. Remember the CpIg, that's what I said. Cp you cannot have. Okay, so this formula is useful because without that you cannot have the PS, PT and PV diagram for oxygen. Okay, for different gases, different materials, we have the separate PV diagram and PS diagram. Unless you are using the law of corresponding states of material invariant chart, that I am not going to discuss here. Choose the reference state. Choose the reference state. Of oxygen to the ideal gas state, at 25 degrees centigrade and 1 bar. Hig, T is 25 degrees centigrade, P equals to 1 bar, which is 0. Sig, T equals to 25 degrees centigrade, P equals to 1 bar. So now we can see that if you have this data, you can easily calculate enthalpy, and slowly you can get the chart, the diagram. The diagram what many books actually have, PS diagram, TS diagram. You might have seen for refrigeration cycle. So now we are actually here to learn how to draw these diagrams. So Payne-Robinson parameters for oxygen. Before that, everything have to fix, otherwise you cannot proceed further. Payne-Robinson parameters for oxygen. Payne-Robinson parameters for oxygen, which is AT 0.45724 R square PC square by PC alpha T, BT, which is 0.0778 RPC by PC alpha T, which is 1 plus kappa into 1 minus square root of P by PC whole to the power minus half. Where kappa is 0.4069, PC is 154.6 K for oxygen, PC is 5.046 megapascal for oxygen. So these parameters, once these parameters are known, that's it. So we have all these parameters required for your departure formula and for calculation. Remember that we have to draw three diagrams. PV diagram, we have to draw PS diagram, we have to draw PS diagram. So for PV diagram, what PV diagram looks like, you know how it looks like. Of course, we have not done earlier based on the Page relation. We have done for the Van der Waals equation PV diagram. And PV diagram looks like this is your pressure axis, volume axis. The critical point, and then okay. This is your saturation pressure. So first question was to draw this diagram. First question was to draw this diagram. So how to proceed? Earlier I used to give assignment. 2-3 years back, in the course we used to have 10 marks per assignment, computer assignment. So students used to do that, but these days I am not asking. If you want, you can do that, but it is not mandatory. So we have P equals to RT by B minus B minus AT by B into B plus B plus B into B minus B, or we can write B square plus 2B minus B square, whatever way you feel comfortable. From this, one can have Z polynomial. So you go back to your Carnot's method and supply me the coefficient Z cube, Z square, alpha Z square beta Z plus gamma equals to 0. So what are the terms? What are the coefficients for Z square? Coefficients for Z square. Ping Robinson, yes. Ping Robinson. So, yes, who can volunteer? Yes, madam. Minus 1 plus B. Z.
A minus 3B square minus 2B.
A minus 3B square minus 2B. And constant term?
Minus AB.
Minus AB plus B square plus B cube. Minus AB plus B square plus B cube. And here we know that A equals to AP by RT whole square and B equals to small b capital P by R. And of course, we know that if you know Z, which is PV by RT, and by knowing P, R, and T, you can get. We have done the calculations earlier using Carnot's method. We got 2 roots actually. Remember. So there are 3 cases: case 1, case 2, case 3. We have done delta and all those things. So in the nicely, you can, if you write a program, you can nicely write a computer program. In the program, you can actually write different subroutines. You can actually have a subroutine for Carnot's method, for case 1, case 2, case 3. Calculate the determinant, and based on the determinant greater than 0, less than 0, equals to 0, we can have 3 subroutines. Those 3 subroutines can be called. Calculate the Z. If you have the 2 roots, particular pressure, you can have particular volume. Okay, like those. If you have 1 root, basically we can get all these things. These are basically called isoforms. Okay. I am not asking that. Earlier I used to teach how to write a computer program. I used to give algorithm, but now I am not asking because we should enjoy life. Why to have so much? So I thought that there is no point, and students never appreciate it. They thought it is too much of load. I thought, okay, fine. If you don't want, I don't want to. So that's so your headache is reduced. But I thought this should be included in the syllabus. How to do that? That is important. As a practicing chemical engineer, when you go for job interview, you should know. In fact, job interview, if you have a computer program and show it to them, yes, I have a thermodynamics course, and in fact, I remember that one guy, MTech, several years back got a job in GE, and he told me, sir, your course is very useful. I said, why? No, you get the mini project, a computer program. I did the computer program. He got 10 out of 10 in the computer program. And the job interview, he didn't discuss about his MTech project. He discussed only his mini project, what he did with me, the coursework, and he got the job in GE. So that's what my intention was, that these computer programs, it will give you avenues to get job, but unfortunately the students don't like it. They think that this course is too much loaded, pressurized, and of course I removed it. So I don't know whom I am favoring. Anyway, so when you develop a computer program, so here there is the algorithm. I want to give the logical steps. If you want, you can actually write a program, develop a computer program, and you have to have this diagram. If you have all these diagrams, then you can, that's it. You can actually have this exact thing. Our objective is to have this diagram. So for this diagram, remember that you can start the pressure, slowly come here, pressure. Okay? Here temperature is fixed. Okay? So what you can do, you can have a table, temperature, start from minus 100 degree, minus 75, minus 50, then you can have 50, 75, 125, 150. That means each set will give you each of this curve, because these are called also isotopes in PV diagram. Along this line, temperature is constant. So if we have this data, this particular column would give particular line. The point is, at this point you should get 2. So how to do that? You fix pressure equals to 1 bar. Okay? And calculate Z, V, H, S. Here is Z1, V1, H1, S1, some value will get. My pressure is 1 bar. If I fix a pressure, temperature is fixed. If you look at the equation, okay, here A is depending on the A is known from that expression. P is known from here, 1 bar. R is known, and temperature is already known. You have to be very careful the units. If your units are good, because the units are not reached here. If you don't have proper units, that's why I always say that you write proper units every time. If you don't write, you won't get that kind of thing. So if you do that, you can get the solution. Okay. So we have Z1, and from Z1 one can calculate V1. Okay. And from departure, you come here how to calculate H1, S1. This is still question mark. I have not discussed, but this is pretty straightforward. Calculation of Z1 from the Carnot's law. Similarly, one can have Z2, V2, H2, S2. One can have Z3, V3, H3, S3. When a pressure has been fixed, for different temperature, you can store the data in your MATLAB or Photon file. Right? You store the data. Next, you select another pressure, 2 bar. Next, you select another pressure, 2 bar. And do the same thing. Calculation of Z, V, H, S. P 5 bar, then you can put P 100 bar and do that same Z, V, H, S. You select the pressure just to see how you want your data to be stored. How you want your data to be stored. Okay. So next question comes your phase boundary. The phase boundary is this one, because where you get two roots. So this is your first table. This I will say table A. This I will say table A. Now we will discuss table B. Now we will discuss table B. So table B discuss the simple if you fix temperature for different pressures, how to calculate ZBHS. Table B talk about the vapor liquid phase boundary. Table B, which is the thermodynamic properties. Thermodynamic properties of oxygen along vapor liquid phase boundary. Vapor liquid phase boundary using Bain-Robinson equation of force. So we have temperature degree centigrade minus 200. We have pressure ZBHS minus 119. Again pressure ZBHS minus 170 minus 125 minus 100. So what are temperature? Particular temperature. Okay. So from here we can actually calculate. From there you can actually calculate what are the if there are two roots, you can calculate ZZ and ZL. Highest will give ZZ, lowest will give ZL, and that will give you VG and VL. That will give you VG and VL, and that will obtain the particular pressure. You may miss it out. What actually happens sometimes, because you will appreciate better if you write computer program. I am here unfortunate or helpless. Without computer program, I have to talk to you something which we can expect from computer program. Earlier people used to write the program, they used to have a lot of interesting episode. What actually people get? They get solution. Suddenly they are getting solution here. Because this will occur at particular pressure, maybe 143.33 bar or 33.33 bar. If you go 33 bar, you won't get. You will get here. If you get 32 bar, you will get here. Okay. Sometimes people do mistake. They find somehow something here and join, and that's it. If you join something, because of the Maxwell equal area rule, if it is not equal, then your entire thing is wrong. So you get scattered data. You get scattered data. So particularly to get this line, you need to have the pressure. That is called PSAT, saturation pressure. That is by trial. How will you get? You don't know. You are getting here, you are getting here. So basically what actually happens when you are in this regime, we generally go up. For example, you are getting here, pressure say 40. You are getting here, say 30. Try out 35. Okay? Just see whether you this branch or this branch. By half and half and half, you will get approximately two solutions. Once you get two solutions, that's it. Generally, you won't get two solutions here. You will get complex or real. This zone, you won't get two solutions. That's what I'm saying. If you don't do by yourself, you won't feel. I can feel because I know how to do it. This branch you get only one solution. Real solution. Other two are complex. This branch you get only one solution. Others are complex because it's based on delta. based on delta. Or you can ask the computer program, calculate delta. When you want to find it out, instead of getting the roots, you just try to half it, calculate delta. Delta is still not less than 0, it is equal to 0, greater than 0. Half it. Okay, yeah, I am getting delta less than 0. Calculate and you get 2 roots. And that's the line you get. This line is very important. This will occur in a particular window. Maybe 36.33. You slightly part of, you won't get 2 solutions, you get only 1 solution. Either this much or this much. Sometimes people do mistakes. Sometimes you actually get this kind of superficial amount, they do like this and the entire thing will be wrong. You have to be very careful. So it is easy to get this bunch. It is easy to get this bunch. When it comes, you have to do trial and error. A computer program quite easy. Just half it. So 40, 30, half is 5, 35. Approach from here or approach from there. Whatever. You fix up. You may be approaching from there. 35 plus 30. How much it is? Or whatever. 32.5. So approach. Better to go by this is better. On the thing you can easily monitor. So for 35 and then still what's here. So some point you can actually get. It will come 0.5 maybe. It will be 0.125. And that accuracy you can actually get. Delta less than 0. Once you get delta less than 0, that is the point where you are getting 2 or 3 real roots. You are getting 3 real roots. If you look at Cardan's method, one particular case you are getting 3 real roots. And that will happen only and only vapor liquid equilibrium case. Which will not happen for other region. Right? Clear? So that will give an idea. That gives an idea how to get the entire diagram. There is a better way to do that. When I will talk how to get the saturation pressure. It's a much better way. In that case, later on, what actually people used to do that, they used to write a computer program, then when they know the better method, they teach later on, using fugacity, then they replace the subunit, use the better method, which does not require any such trial and error. You can directly get it. There is a way to get directly saturation pressure. This is called saturation pressure. If you get it, your job is done. So I think construction of PV diagram is clear. In many books you see that they are having this diagram. The first time you have done, how to draw this diagram. Now you should not get scared. Any of the book you just pick up, you just see this kind of diagram. You just say, yes, I know. I can write a computer program, do the trial and error iteration, and I can get that kind of diagram. Next I'll be talking about the enthalpy, pressure, enthalpy, or the pressure entropy diagram, whatever pressure enthalpy you can actually look into. So we'll go for the pressure enthalpy diagram, and for that purpose, just delete this part. We have the departure formula H minus Hij which is P1 bar and T25 pixel equals to H minus Hij Tp plus Hij Tp minus Hij P equals to 1 bar, T equals 25 pixel. If I have taken it, I know this is 0. I have already assumed it. But my departure formula is H minus Hij Tp. This is the departure. This is the departure formula. Right? So this formula is known, H minus Hij Tp, and Hij Tp minus this. What should I write? This delta H It. It will be what? Delta H It means what? Delta H It means what? We know that? Delta H It means what? Delta Hij. Delta Hij equals to, very simple, we have done in the school level. The school level question I am asking. delta HIG equals to CPIG delta T. If I say like that in the class, you will say that teacher is bad, not writing, not saying properly. If I say CPD, CPIG, because CP you cannot measure. CPIG. So it is T 298.15 degree Kelvin to T CPIG. Okay, and this will give, of course, H minus HIG TP. Already you have the formula handy, and this formula we have derived today in the class for Payne Robinson, right? This formula already derived in terms of Z minus 1 and Z is actually being calculated from the table A. And you get this term, this is new term, which is CPIG, already the formula given today in the class, which is the 25.46 plus 1.519 10 to the minus 2t minus 0.7151 10 to the minus 5t square plus 1.311 10 to the minus 9t cube. Okay, and this gives the calculation 25.46 into t minus 298.15 plus 1.519 10 to the power minus 2 by 2 into t square minus 298.15 square minus 0.7151 10 to the power minus 5 by 3 into t cube minus 298.15 cube plus 1.311 10 to the power minus 9 by 4 into t to the power 4 minus 298.15 to the power 4. And that is your nothing but H, because HIG of this equals to 0. So H you got. Now some nice formula. Something interesting, something nice you got now. How to calculate enthalpy at a particular temperature and pressure? There's a formula. H equals to H minus HIG TP plus the whole lot of stuff, and I'm using CPIG, form of the CPIG. Okay. Next step. So we have, I'm trying to recall the formula for the Payne Robinson. You already have it handy, which is H minus HIG TP, which is Z minus 1 RT plus T dou A by dou T minus AT by 2 root 2 B ln of Z plus B into 1 plus root 2 divided by Z plus capital B into 1 minus root. Okay. So this will be plugged in here. We can calculate. So if you look at the table A and B, table A has temperature fixation first, pressure fixation. With that you can calculate Z. Temperature is known. This quantity will be known. This is dou A by dou T. We already we can do the calculation. Dou A by dou T, AT, B is everything is known, and this everything is known, and you can get set of H and H. Similarly, one can calculate S minus SI. So this is done. So your H part is solved. So you have ZPHs in table A. Z is known, B is known, H is known. Next comes S. How to calculate S? To calculate S, same thing will go for, because we also assume that SIG P equals to 1 bar, T25 degree centigrade goes to 0. So S minus SIG T25 degree centigrade P equals to 1 bar, which is S minus SIG TP SIG TP minus SIG T 25 degree centigrade P equals to 1 bar. And what is this?